Hey everyone. In this discussion, we're going to talk about how we can use randomness in algorithm design. So the first problem we're going to work on is about universal hash tables, and it's going to be very similar to polynomial multiplication verification and also matrix multiplication verification. So these are actually problems that are used quite frequently, and the analysis we're going to do is very similar. So if you want to see more applications of these techniques, you can check out the book Probability in Computing, and they'll go through this example in chapter 2, and it's very similar to what we're going to do. So let's get right into it. The first thing we want to do is we're going to look at this specific kind of hash function. So it's parameterized by a matrix, M, and M is binary, so it only has 0 or 1 entries, and the dimension of the matrix will be L by K. In particular, for this problem, our little m that we're going to discuss will be 2 to the L, and that's how we're going to prove things about universal families of hash functions. So we have this special kind of hash function. It's pretty simple. We take our vector x, this is our input vector, it's going to be k-dimensional, and then we're just going to multiply m by x, and that will be our hash value. So in particular, we're going to actually get out an L-dimensional vector. So this won't just be a single number like you may be used to with hash tables, but it'll actually be a sequence of numbers. But that's all fine, and we can still talk about different families. So the main thing we're going to use here is the principle of deferred decisions, and I'll talk about that a little more in a second. But first, what we're trying to prove is if we choose M uniformly at random, which means we choose every entry uniformly at random, then this set of hash functions is a universal hash family. And that just means if we take two different possible inputs, then the probability over all possible hash functions that there's a collision, so that the two hash functions, or so that the same hash function actually will have the same value for these two different inputs, this total probability has to be essentially uniform. So behaves and gives an exact value of 1 over m. So that's what it means for a family to be universal. There's other definitions we could use, but this one's going to be convenient for our purposes. And the intuition behind universal hash functions is it just gives us a very nice formal definition of hash functions being nice. So this was just a definition picked so that the hash functions are essentially nice. So the reason we picked this is based on a bunch of theory that if you're interested in, you can check out Jeff's notes on hashing, but otherwise we're just going to take this definition for granted. So to prove this claim, we're first going to prove this lemma. So this lemma is just about a very specific type of function and vector relation. So it just says if we pick one of these hash functions uniformly at random, and then we plug in some x into it, then the probability it's equal to 0. So under this specific value x, our hash function takes on value 0 will be exactly 1 over 2 to the L, which is the same as 1 over m. So essentially we're saying it's, in a sense, uniform for the collision probability in the specific case where we're just looking at 0 instead of having two hash functions, for example. So why do we care about this? Well, in particular, if we do take an arbitrary x and y, and if we look at the probability over possible choices of the matrix M, that hm of x equals hm of y, then this is exactly the same as the probability over possible m's of mx equal to my, and so this will be the same as the probability over m that m times x minus y is equal to 0. So in particular, if x and y are different, and that's all we really usually care about, then this x minus y will not be 0. It'll have some entry that's not 0. And so this lemma will tell us that this is exactly 1 over m. So in particular, we have here that x is not 0, which just means at least one entry of x is not 0. Because remember, x is a vector. So that's what it means for it to not be 0. And again, the 0 here as well is also referring to the 0 vector. Okay, so once we have this lemma, we're done. So now let's prove the lemma. So the way we're going to prove this lemma, we know x is not 0. So there's at least one position, j, such that xj is equal to 1. So in particular, we know that x is not all 0, and so we can relate the entries of m to each other to figure out what the probabilities have to be. So this is where we're going to talk about the principle of deferred decisions. So specifically, let's look at this product mx. We want it to be equal to 0, and in particular, we know xj is not 0. So assume we've already picked the entries of m. So let's assume m's entries are all chosen, except for mij. So we're basically going to ignore the other entries of m except for this one and use conditional probabilities to figure out what the probability of this whole event is based on just the probability of this specific entry taking on a certain value. So in particular, we know that for the row I, so if we fix row I, so I is between 1 and L, so we know that mij has to be equal to minus the sum of all the other entries in this row. So if we sum over all k from 1 to L, where k is not j, then if we take mij, or mkj, or mik, this times x, I, divided by xj, must be equal to mij. So this is just because, by definition, mx of I, if we just look at the ith row, this is exactly the sum of all k equals 1 to j of mik times xk. And we know this is going to be equal to 0, since we're trying to get mx to be equal to 0. So in particular, if we know the whole row sums to 0, we can relate this specific entry in terms of all the other ones. And because xj is equal to 1, this is well defined. So this is because xj is equal to 1. We can do this division. So in particular, the probability that this specific row is equal to 0, conditioned on the fact that we already know all the other values of m for this row, this will boil down to the probability that mij is exactly equal to this quantity here. And this probability is exactly 1/2. So remember, we choose m, in particular every entry of m, uniformly at random. So the probability that mij has any particular value will be 1/2. So if we condition on everything else being chosen in m, we know the probability that mx of I equals to 0 is exactly 1/2. So the probability that mx of I equal to 0, given that all of mik for k not equal to j are determined, this will exactly be 1/2. Okay, so we got a conditional probability. Now the last thing we need to do is use the law of total probability. So this will allow us to essentially sum over all the other possible values of k, and it'll basically eradicate them. So once we use the law of total probability, this will give us a sum of conditioned events or intersections of events, which will just give us that the total probability that mx of I equals 0 is 1/2. So this is by the law of total probability, and that gives us something closer to what we want. So now we know that for a specific row, its probability is 1/2. Now the key thing here is we choose m uniformly at random, and so we also choose each row uniformly at random. In particular, if we restrict any sort of uniform random variable, it'll still be uniform. So because we know this relation for all the rows, and they're all independent as well, we will have the probability that our whole matrix mx equals to 0, this will exactly be the probability of the and of all rows. So I equals 1 to L, that mx of I equals to 0. And then because they're all independent, as I just mentioned, this will become a product. And now we know these are each 1/2, so this will just be 1/2 L times, which is the same as 1/2 to the L, which in our case is exactly 1/m. So thus, the lemma is proved, and so we can go back and complete the proof of the entire theorem. So this shows us that this specific family of hash functions is in fact universal. And we used the concept of principle of deferred decisions. So again, if you want to see this concept used more times, check out the book Probability in Computing. And that's all for this problem.